Howdy, stargazers, and welcome to this episode of Star Trails. My name is Drew, and I'll be your guide to the night sky for the week of April the 26th to May 2nd. This week, we're exploring a side of the universe you can't see, at least not directly. I sit down with Professor Enrique López Rodríguez, one of the leading researchers in the United States studying magnetic fields and galaxies, to talk about the invisible structures that shape the cosmos. Later in the show, we'll take a look at this week's night sky. Whether you're tuning in from the backyard or the balcony, I'm glad you're here. So grab a comfortable spot under the night sky and let's get started. We tend to think of galaxies as massive collections of stars, bound by gravity, pinwheeling through space. But beneath that visible structure, there's something else at work. Invisible magnetic fields stretching across thousands of light years that are quietly shaping how galaxies evolve. In fact, as you're about to hear, galaxies don't exist in isolation at all. They can exchange material across vast distances, guided along these magnetic pathways. And at the centers of many of these galaxies are supermassive black holes, some actively consuming matter and blasting energy back into space, and others, surprisingly, almost dormant, as if they've simply shut down. In this episode, we'll step behind the curtain and meet one of the researchers helping us understand the hidden structure of the universe. Today's guest is Professor Enrique López Rodríguez, an extragalactic astronomer at the University of South Carolina, and one of the leading researchers in the United States studying magnetic fields in galaxies. Originally from the Canary Islands, his work focuses on how these invisible fields influence the evolution of galaxies, the behavior of supermassive black holes, and the flow of matter across cosmic scales. He's led major international research efforts, including a NASA SOFIA legacy program to map magnetic fields in nearby galaxies, and has published nearly 90 peer-reviewed papers in journals like the Astrophysical Journal, Monthly Notices of the Royal Astronomical Society, and Nature Astronomy. And as you'll hear, his work is helping us uncover a part of the universe that may be shaping our reality. Here's my interview with Professor Rodríguez. Enrique, thanks for taking the time to speak with me today, and welcome to the show.
Well, thank you for having me.
Tell me a little bit about yourself. How did you get into astronomy?
Okay, I'm originally from Spain, the Canary Islands, these small islands close to South Morocco. The islands are volcanic in the same way that you think about Hawaii to the US, the Canary Islands to Spain. And these islands are very famous in astronomy because we have an international observatory there. Actually, the largest telescope in the world is in the Canary Islands. So therefore, we have a really good skies, like really good skies. I was also very lucky that the university in my hometown have astrophysics degree, so I didn't have to move because I was not able to go anywhere because my family didn't have enough resources to send me to another school. So then I did my bachelor in the Canary Islands, and then one of my professors told me about this exchange of grad students from the Canary Islands to the University of Florida. Lucky me, the chair of the Department of Astronomy in the University of Florida was from Spain. So I have a phone call with him. And then I think a month later, I was in Florida, just doing the PhD there.
Well, so you come by it honestly. You had very dark skies growing up, and it inspired you.
Yeah. That was very, very interesting there.
Well, let's get right into it. You're an extragalactic astronomer. Can you tell us what that means? Because that is a fascinating term.
Yeah, so I'm basically studying the galaxy evolution. So I'm interested to know how galaxies form, what are the compositions, and then how they evolve from the beginning of the universe to nowadays.
How did you get into that? That is a very specific field.
Mm-hmm. So when you think about the universe, the main most common objects besides stars are galaxies. And then we always hear from the news or when you read books about the universe is expanding. Einstein have the general relativity that explain the whole universe. They're like, all right, so this is interesting, but what's inside of this universe? And we know we see people here, we see cars, we see stars, we see the planets, but then you start getting more interested, like what is beyond that? And you see that beyond the solar system is more stars. And beyond more stars is all inside of objects that we call galaxies, that are all gravitationally bound by the motion of stars orbiting around the center of the galaxy. And then when you go beyond that, you see there's not a single galaxy that we live. It's like thousands of them nearby to the Milky Way. You go a little bit larger and zoom out, and it's like, okay, it's several trillions of galaxies moving inside of space, and they're all moving away. I'm like, okay, now I want to know about this. So like, I want to know about the big picture, how this even form. Are galaxies the same? They're not. Why they are different? And what they make them different. And then how galaxies collide to each other, or how they destroy each other, how they form. And then I get into a rabbit hole. And I've been in that rabbit hole for the past 20, 30 years until now.
And that rabbit hole is the study of how magnetism affects galaxies, correct?
Yeah, exactly. So then you have another level here. So normally when we observe galaxies or the universe around us, we observe the radiation, the photons emitting from these stars, for example. But electromagnetism tells us that if you have charged particles moving, those charged particles generate a magnetic field. And those magnetic fields cannot be destroyed because monopoles don't exist. So then like you cannot destroy. The only thing that you can do is amplify them, meaning that you have more magnetic field lines per volume, or you can dissipate them. And that means that you spread the magnetic field in a larger volume, but you cannot completely destroy them. So that means like, okay, so if we are in a permeated magnetized universe, what is the effect of this magnetic field? So how the magnetic field affect the formation of stars, how affect the dynamics of the gas, how affect the accretion onto supermassive black holes. So I got more interested into that. So because you have the connection between physics that you can explain in the lab by a magnet, and you put the iron dust around, and then you also connect the astronomy side, like how stars form. And then I've been for the past 15 or 20 years try to estimate what is the effect of the magnetic field in the dynamics of the gas into supermassive black holes in the center of galaxies or in star formation. And it looks like that they're very, very, very tiny energy of magnetic fields, but they're extremely important to explain how stars form, for example.
Well, and you mentioned it yourself, galaxies are these groups of stars bound together by gravity. And in astronomy, we talk about gravity all the time, and gravity's, not that I can do it, but relatively simple to calculate if you know the mass of something. How do you calculate magnetism from afar like this?
Right, yeah, so exactly. Well, gravity is the one that governs the whole formation of stars. For example, you have a mass, and gravity makes them to collapse. Okay, so now how do you measure magnetic fields? So we cannot send a magnetometer anywhere. So what we observe is the effect of magnetic fields in material. For example, let's say that you have an electron. An electron is a charged particle with negative charge. So if you have a magnetic field, those electrons need to move along the magnetic field orientation. So have a specific trajectory, and these electrons are spinning around the magnetic field. So then we can measure that direction of the electrons that give you a specific signature in electromagnetic wave. And then measuring that signature that we call polarization, we can say, okay, this electron is not freely moving in space, it's moving along some direction, and then we can infer the magnetic field strength and the orientation of it. This is one way. And then the other way that I'm using for the past 10 years, I use dust. And dust is organic compounds made of carbon, nitrogen, oxygen, silicates, and iron. And these compounds are like micrometer size.
Okay.
And because they have iron, they align with the local magnetic field. Let's imagine that you have a lot of rice grains, and they're elongated, right? And these rice grains have irons inside. So then if you put a magnet around, they will all align with the local magnetic field. And this is exactly what I'm observing in very far away galaxies. I see like all this dust aligned with local magnetic field.
This reminds me of course, the elementary school science experiment. You put a magnet down and put a piece of paper on it and put some iron filings, and you see the pattern of the magnet.
Exactly. You don't see the magnetic field. You see the effects of the magnetic field in matter.
Okay.
And this iron that you mentioned is exactly what I observe in galaxies.
And how are you observing that from so far away?
These dust grains have a very interesting property. So they're micrometer size.
Okay.
They are very close to stars. The stars are radiating energy, mainly in the optical and ultraviolet.
Okay.
And then these dust grains absorb all that radiation. And when they're absorbing, they get heated. So then they have some temperature. If you have a temperature, then they are emitting radiation.
Okay.
Because it's a black body radiation. So then if they emit a radiation, the only thing that we need to do is to build an instrument that is sensitive to that specific temperature.
Okay.
And then we can observe the radiation from those dust grains.
Fantastic. And what instruments are you using to accomplish this?
Yeah, so many years ago, I used to work for NASA. So it's a project called SOFIA, so the Stratospheric Observatory for Far Infrared Astronomy. So we had an instrument called HAWK Plus, and this instrument is very, very sensitive to cold temperatures. With this instrument, we put it in the back of a Boeing 747, very highly modified Boeing 747.
Okay.
All German engineering, because the Germans are the great engineers that collaborate with NASA. And then we used to fly at 45,000 feet over the sea level. And the reason is because you need to go outside of the atmosphere.
Okay.
And it's cheaper than sending a spacecraft.
Right.
So then we had this new instrument. We didn't know that works, so you cannot send it to space. It's all exploratory work. And the idea was to exactly observe magnetic fields in the universe. So we put it in the back of the Boeing 747. We flew the stratosphere like a few hundred times. And then we took observations of nearby galaxies. Since day one, we start tracing those magnetic fields at large scale. So we see that this very tiny fraction, like micrometer size, are able to, dust grains are able to provide us the information of magnetic fields of several thousands of light years. So we are doing microscopic physics to get microscopic tracer of the magnetic fields.
Speaking of working for NASA, I've seen your name attached to some images that I've seen on NASA's website, and I believe these are the images that show a galaxy, and you can almost see those magnetic lines that are sort of superimposed on that. And so that data collection you're talking about is how you produce those images.
Yeah, exactly. So I have a program called SALSA. Well, it's coming from my Spanish heritage. I wanted to call SALSA. It's the SOFIA Survey for Astronomical Magnetism. I got observations, archival observation previously done by NASA in the optical to see the stars, in the UV, to see the star formation, in the infrared to see the dust, and combine them, all real observations. And then on top of that, I put the magnetic field orientation. It looks like the starry night of Van Gogh. There right away, you can see, for example, the galaxy's spiral, you see a spiral magnetic field. And then you see the spiral is more chaotic exactly in the region that you have a star formation. So now just visually you say, oh, something going on here. So why I don't see this spiral? And then you go further and say, oh, the star formation is tangling or disturbing the magnetic field. And now like, all right, so then should be a relationship between how the star formation is doing in the terrestrial medium with what we know with the magnetic field.
Well, I love that you mentioned Van Gogh, because when I looked at those, I thought they do look like artwork. I don't know if you've ever thought about it, but you should blow some of these things up and do a gallery exhibition.
I should. Yeah,
you should do that.
This is one. Yeah, I need to do that. Yeah.
They're really beautiful images, and of course the galaxies themselves are beautiful. But then being able to see that dynamic of the magnetism that you've traced on there. It's really incredible. And you're right; they follow the spirals. And that's a good place to talking about centers of galaxies, because that's something you specialize in as well, right?
Yeah, so what we can do is like we can observe galaxies that, like, for example, spiral galaxies. They're very quiescent, but they're very normal between quotation mark. And then we know that you have spirals and there is no much star formation. And this, you can use it as a sample, as a control sample. And then from there, you can get more exotic, meaning you can go to galaxies that has a lot of star formation and is creating a lot of supernovae explosions. In this case, when you compare with the spirals, trying to have a spiral magnetic field, now you have the magnetic field to be pushed away from the galaxy. And I was like, whoa, okay. So you have 10, 20 supernovae that is exploding in the center of the galaxy. And there's not only pushing dust and gas outside of the galaxy, it's also dragging the magnetic field away from the galaxy. And now, like, okay, now it's not only the galaxy, it's also the surrounding environment of the galaxy is also magnetized. Or like, all right, okay, now we know that you have magnetic fields in the intergalactic medium. And again, if you have charged particles, they have to move through those magnetic fields, so they cannot move freely. So now we know that we can trace in the magnetic field, we know how the material flow from galaxy to galaxy. That's one way. Then you can get more exotic too. And then you can get galaxies merging. And you have two galaxies in interaction. And then like, okay, how the interaction make so what happened with the magnetic field? And when you see these interacting galaxies, maybe they grab one of the spiral arms and stretch it and compress. And then you see the magnetic field also are stretching and compress. And you have like a bridge between those two galaxies with a very strong magnetic field connecting both of them. And that means that if you want to transfer material from one to another galaxy, you need to go through those magnetic fields, mandatory. Too. So they cannot go and move freely and then fall using gravity. It's just they have to move. The gravity is taking place, but they have to move through those lines.
That is incredible that there are those connections, because I'm imagining we're talking about very, very long distances between the two, but yet they make that connection.
Exactly. Yeah, I mean, we're talking about, our Milky Way, the galaxy that we live in, is like 15 kiloparsec or so in size. I don't know, 30,000 light years or something like that, around there. So these two galaxies are like 10, 20 kiloparsec away from each other. And now you're talking about a magnetic field that's connecting both of them of the size of the Milky Way.
Wow, that's incredible. Yeah. Some of your more recent stuff is about the idea of these galactic outflows. Is that the process you were describing just then, about how they travel between galaxies on these waves of magnetism?
Yeah, right. So exactly. So this is like galaxies, but then there are some galaxies that we call active galactic nuclei, so AGN. And these galaxies are powered by accretion onto a supermassive black hole. And this is where my thesis was about. So my thesis was about trying to trace the magnetic fields surrounding supermassive black holes. So the reason behind that is because every single model that explains how matter goes into a black hole requires the need of a magnetic field, but has not been observed yet. And then like, okay, if there's some material, maybe this dust, I can trace the magnetic field using this dust. And I've been doing that for the past 20 years or so. I trace the magnetic field. So you have the supermassive black hole, you have material in a disk orbiting around the black hole, and the material is highly magnetized. And I trace the magnetic field and I measure the magnetic field that looks like a donut shape, like a circle.
Like a donut.
Like a donut, exactly. Yeah, okay. So, but then when we see these active galactic nuclei, we see that the AGN are also expelling a lot of material. And this expel of material, we call it outflows. The black hole, we always say the black hole is nothing can escape the black hole, but actually the black holes are very inefficient eaters of matter. So actually like 90% of the material that go into the black hole goes away in form of energy. So only 10 or less than 10% go inside of the black hole. And that 90% of energy need to be released somehow. and that somehow is due to magnetic fields. So you can imagine, for example, solar flares in the sun. Yeah, and then it's a lot of satellites that try to figure out how the sun is expelling a lot of plasma. And then when you see the very detailed images, you see some kind of like arcs. So they call a flare.
Yes.
And these arcs, and then this arc kind of like break and then release the energy. Those arcs are created by magnetic fields.
I feel like I remember seeing that. Yeah, the little loops that appear on the sun's surface are created by magnetism.
Exactly, and those loops open, like break, and then release the energy. This is exactly what happened in the disks around supermassive black holes. You have these loops on top of the disks, and then the disks have those loops break, and then release energy. And that's what we call outflows.
Okay.
So, and then those outflows, of course, have a lot of energy going out. You have a supermassive black hole, you have a lot of energy, you have a lot of magnetic fields, you have a lot of mass, and that outflows can do few things. One is that they don't have enough energy to leave the galaxy and then fall back into the galaxy, and then you feed again the black hole, or can go into the intergalactic medium. So I'm very interested to know how these outflows evolve as a function of the power of the galaxy.
It's amazing to think that they can actually escape the gravity of a galaxy like that. How does that happen, do you think?
Well, there's a lot of energy being released, like a lot of it. So then it is about what is the velocity that you push into the system at the beginning when they're released, and the velocity is larger than the gravity.
Okay.
Escape velocity is larger than the gravity, so then they can escape. I mean, we can send, not the same, but we can send rockets to the moon, right? So we put a lot of energy in the back of a rocket to push it out. So you can imagine a very extreme case scenario that you have a supermassive black hole with a lot of radiation. Sometimes you push a lot of material away and have enough energy to leave the gravitational potential of the black hole.
And that energy, just like you said, it just dissipates into space, or it gets grabbed by something else.
Yeah, exactly. It can go into the intergalactic medium, the medium between galaxies, if have enough energy, or can travel a little bit above and below the disk, and then fall back due to the gravity and at larger distances from the galaxy.
And you've tracked this at the supermassive black hole at the center of our galaxy, correct?
Yeah, I do our own galaxy, but our own galaxy has a black hole that is not accreting any material, so it's basically dead. There. The reason is because there's no material surrounding the black hole. Maybe in the past, the black hole was very active, and then it was like pushing out the material, but right now it's just there, very quiet. And there's some material around, but it's not really going into the black hole at all.
That's amazing that, black holes, once upon a time being these theoretical objects, and now you can look at them and say, well, this one's not as active as this one is, and this one is doing more than that one. Mm-hmm. That's incredible. I've always been curious. We think most galaxies have a black hole at the center in some cases. Is that what force that creates the spiral shape of the galaxy itself, you think?
Yes, so we think that most of the galaxies, if not all, has a supermassive black hole in the center. Supermassive means 10 to the 6 to 10 to the 9 times the mass of the sun. So you have a million times of a few billion times the mass of the sun inside in the center of the galaxy, of a size that can fit inside of the solar system. So this is the size of the supermassive black hole. Okay, so this black hole has a gravitational sphere. So meaning like how far away you need to be in order to be affected by the gravity. And that is only the very, very central part of the galaxy. So even though we see spiral galaxies, these spirals are not spiraling around because of the black hole. It's spiraling around because of the angular momentum of the disks. So let's say, for example, that you have a spherical cloud. That the spherical cloud collapse, and when it collapse, have some rotation, and then form a disk, and that disk start rotating. And that's the reason why we see the spirals moving. But it had nothing to do with the black hole.
So it's not like this science fiction visualization of a black hole out there swirling around like everything swirling down a drain. It's not like that.
Yeah, in the central part of the galaxy, yes. In our distance from the center of the galaxy, we are not related with that.
Okay.
Yeah.
That's fascinating stuff.
Even though we are not affected by the gravitational potential of the galaxy, the dynamic of the galaxy or the evolution of the galaxy depends of what happened with the black hole. So if the black hole is active at creating matter, so that means a lot of energy being released. So that energy can affect the dynamic of the galaxy. For example, if our galaxy have a active galactic nuclei in the center, we will not be here, for example, because so much energy that it will destroy the solar system.
That is incredible. That is incredible to think about. What does a modern astronomer do? What does your day look like? Because I imagine, especially with the work you're doing, you're not looking through telescopes maybe at all anymore.
Mm-hmm.
So what does your day look like? You have an idea. How do you chase it?
All right. So my position as a faculty is a combination of research and teaching, right? So the teaching, well, I have several classes during the year, and then I teach all the way from no science majors about what astronomy is. For example, in this semester, I'm teaching the dark universe. So it's about I call it our ignorance in the universe. So we don't know about dark matter, we don't know about dark energy, we don't know about expansion of the universe, and then I just show them what all this means. And then on my research side is research projects, right? So like I have research goals. For example, my overall goal is understanding magnetic fields in the universe. So, and I observational astronomer. So I use telescopes. So then I normally during the year, I have to apply for observing proposals to use a specific telescope all around the world. For example, today was the deadline for a telescope in Chile. It's called ALMA. It's the Atacama Large Millimeter Array. And then those ones allow me to, for example, observe the magnetic fields in the early universe or very, very close to nearby AGN. So I write those proposals. It takes me some time. Of course, sadly, you cannot go to the Atacama Desert, but they give you the data. For example, I also I use telescopes in Hawaii, in the Canary Islands, Spain, Chile, and South Africa.
And when you say telescopes, we're talking radio telescopes?
It's a combination of optical telescopes, infrared telescopes, radio telescopes. So that means that my day-to-day life is writing, observing proposals to get new data, to go deeper into specific fields, or to do, for example, a large sample, because I want to have a statistical sample of multiple galaxies. And then also, I have my research team, have grad students and postdocs. So that means I need to find funding to support them. So that means I need to apply for national grants, for example, the National Science Foundation or NASA or some private foundations that I gain. So I submit some proposals, say this is the research that I want to do, it's important for whatever reason, and then please give me some money so I can pay some grad student for the next 2 or 3 years.
So like you said, you were working with ALMA. So you get your data back from ALMA. What's the next step?
Oh, the next step is be very excited at first, like have new data. Now, like what this data is about. So because like every single time that I observe with a telescope, in this case ALMA, they give you new things. And you spend the next year or 2 years analyzing the data, quantifying the data, meaning like you have to do a lot of statistics to make sure like how robust your measurements are. And then once you have a result or that you are convinced that is real, so then you need to have an interpretation, a scientific interpretation of that. And that requires a lot of communication with a lot of collaborators, besides to yourself and the team that I have here, like what this all means. And then you have a lot of conversation with many people just to have a consensus and not be biased by my own ideas too. And then when I have a very robust interpretation, so then it's a matter of like writing the the paper and publish it, and then show it to the community, and then see what they think about it.
What has you the most excited about where the field of astronomy in general is right now?
So it's very exciting to have the James Webb out. Since the launch 3-4 years ago, it's like revolutionizing astronomy. I think the next steps, we have the Vera Rubin telescope in Chile taking data as we speak. I think like the first 3 days they observed like 800,000 alerts of supernova explosions or something like that, which is insane. That means that we're going to have the next 10, 20 years, we have more data that the whole astronomy have been taking in history. And that we have to deal with this data. How do we even analyze tens of millions of galaxies? And moving forward, NASA is going to be launching a few space telescopes in the next few years. So you have the Roman telescope. It's also doing a humongous survey, very deep observation, and you have to deal with the information of millions of galaxies. And now it's a combination of like, how do we use AI to deal with all this data, that we can trust the output of this data, but also what new science can we get from this, right? On the ground, we have Europe and US building the next generation of extremely large telescopes. These are 30-meter telescope in comparison with the 10-meter. So for example, Europe, the European Southern Observatory is building a 42-meter telescope in Chile that's going to be first live, I think, is in 6 years-ish, something like that. So that's all new too. You're going to have like new science. It's not about surveys, it's about detail. So they're like, if you want to know what is happening around a supermassive black hole, you choose that. If you want to know so the new James Webb telescope is observing galaxies in the early universe, you go to the telescope and resolve it and see where the morphology of it. So it's just about the detail of the observations of it. So I'm very excited about the next 10, 20 years of using all this new telescope and see what we learn from them.
So much data, we don't know what to do with it all. Yeah. All the epic astronomy you're doing here, what still amazes you about astronomy?
The pretty pictures. I'm very basic here. I was just like, show me a pretty picture. I'm like, oh my God, this is so great. For my research, it just have a new instrument in a new telescope and get the first light, the first image, which is exciting me like it's no tomorrow. And then it really excites me to know like I have a piece of knowledge of the universe that I'm the first person to have it in front of me, and I need to figure it out. And this is like just I can stay thinking about this for months.
I'd like to thank Professor Rodriguez for coming on the show and being so generous with his time. What struck me in that conversation is just how much of the universe is hidden from us. It's remarkable to think that something as small as a dust grain containing tiny amounts of iron can act as a kind of compass, revealing the structure of these unseen forces that are shaping structures as enormous as galaxies. With research led by scientists like Professor Rodriguez, we're slowly piecing together a universe that's far more dynamic and far more interconnected than it first appears. If you'd like to learn more about his research and see the images we discussed in this episode, I'll leave a link in the show notes. As we close out the month of April and step into early May, the night sky offers a gentle transition from darker, moonless evenings earlier in the month to a bright and beautiful full moon rising at the end of the week. Throughout this week, the moon is in its waxing phase, growing brighter with each passing night. Early on, you'll find it as a waxing gibbous rising in the afternoon and shining well into the evening hours. But by Friday, May 1st, the moon reaches its full phase. This is the flower moon, a name that comes from the abundance of blooming plants this time of year. And while every full moon is worth a look, this one is what astronomers call a micro-moon, meaning it's a bit farther from Earth than usual and may appear just slightly smaller in the sky. Earlier in the week, before the moon becomes fully illuminated, take a moment to look along the line between light and shadow, the lunar terminator. That's where craters and mountains stand out in sharp relief, offering some of the most dramatic views you can get through a small telescope. Now, turning to the planets. This is something of a split sky week, with the brightest worlds divided between evening and morning. Just after sunset, look toward the western horizon and you'll immediately notice Venus, brilliant and unmistakable, shining like a beacon in the twilight. Higher up, Jupiter continues to dominate the evening sky, steady and bright, and still one of the most rewarding objects to observe through a telescope. If you happen to be out before sunrise, there's more to see. Low in the eastern sky, Mercury, Mars, and Saturn form a loose grouping near the horizon. They're not especially bright right now, and you'll need a clear view to the east, but if you catch them, you're seeing the tail end of a quiet planetary gathering that's been unfolding over the past few weeks. Now, this time of year also brings something special for deep sky observers. We're in the midst of what astronomers call galaxy season. The familiar constellations of winter are slipping away, and in their place, the sky is opening up to regions rich with distant galaxies, particularly in the constellations of Leo, Virgo, and Coma Berenices. Leo is easy to spot, high in the sky after sunset, marked by a distinctive backwards question mark shape. Just beyond it lies Virgo, a sprawling constellation that contains an entire cluster of galaxies, some 50 million light-years away. With a telescope, and especially under darker skies, you can begin to pick out faint smudges of light. One particularly beautiful region is known as Markarian's Chain, a gentle arc of galaxies stretching across space, visible as a delicate pattern when conditions are right. And if you're just using binoculars, don't miss the Beehive cluster in Cancer. It's still visible early in the evening and remains one of the most rewarding open clusters in the sky. By the end of the week, the full moon takes over, brightening the sky and shifting our attention closer to home. That's going to do it for this week. If you found this episode interesting, please share it with a friend who might enjoy it. The easiest way to do that is by sending folks to our website, startrails.show. And if you'd like to support the show, use the link on the site to buy me a coffee. It really helps. Be sure to follow Star Trails on Blue Sky and YouTube. Links are in the show notes. Until we meet again beneath the stars, clear skies, everyone.